So there I've just browsed 3 websites, so not much for the demo. And then if I log into the Minimorph, we've got a terminal into Minimorph now, and I can show you that we've captured some HTML files. So if we go user var captures, that's the location. So we've captured 7 HTML files there, you can see. We've only browsed 3 web pages and we've got 7 HTML files, but a lot of them will just be, I don't know, error codes, like 303 error codes or something like that, where the page has been moved or something like this. But okay. the 3 actual HTML pages are in there. I'll be able to show you one of them. That kind of thing. Yeah, yeah, all of that sort of thing. I mean, our parser will actually ignore those, so it won't affect the results. I'll be able to show you one of these. I'll pick the first one. That's actually a big one. It's lucky. So that's just actually the full HTML page of one of these pages. So we've captured it. At this point, what you need to do is analyze that HTML using our document analysis techniques. So if I call up our analyze binary, which is what Peter wrote, let's get that going. You'll get some stuff on the screen about the analysis, and Peter's going to talk to you about what it's actually doing.
So the analysis takes actually quite a long time. So my plan here was to try and talk to you at great length about what's going on and try and buy it enough time to work through everything. First of all, you'll see it's gone through the first 3 files. The first couple it didn't output any keywords for. So that's because, like Jack said, a couple of them there'll be error codes, or even sometimes we found a page which is marked as an HTML and contains a script, or we've just seen the ones with just a line of text. There was one that a website transferred us just hello as a file on its own, and we weren't sure where that came from. So we kick out files that don't start with an open bracket, so that don't start with a tag, and files that are too short, and files that are scripts, and that sort of thing. So that's what happened to these first 2. This third one here is taking a long time over because it's doing the actual processing. It's clearly found that it's one of these. So for each file, the first thing it does is it uses the libxml library to parse it. It parses it into a complete linked list of objects to represent a document object model tree. We can then completely traverse that tree and go through every single node in it. And there's a whole load of tests that we do for each node to see, is it a script, is it a style, or is it going to be interesting content. This is where, in the talk earlier on, somebody asked, could you give more weight to words that are bold or in titles? We could very much do that. So we completely flatten out the tree and save the entire content of the page into one long string. Obviously only looking at the nodes that are relevant, as I just said. Oh, there we go. So once we have the string, we can do the document analysis. You can see it's now finished that page there, and it's output the top 20 keywords from that. So England, cricket, India. You can see it was almost definitely this page, the India via England story. So once we've parsed the HTML into our big long string, we can do the document analysis. This is done in a series of stages. The first thing we do is we do the word frequency count, where we look at each word in turn and we obviously put it into a list, and if it already exists in the list, just increase its count. And then once we've got that list, where we've got every single unique word in the document and a count of it, we then go through that and do this very basic sort of stemming, where we're wanting to remove any plural S's. Like I said earlier, stemming is a huge, huge thing, so we didn't try and go into it in too much detail. So we look through the list, and if a word ends with an S, we view the rest of the list first, before we look at our statistics file. We view the rest of the list to check that if the version without the S also exists. Because if that does, that means that's a word, so we merge the 2 scores of those. For doing the weighting later on, we have a big, big list of frequency statistics from natural language, which we use as a dictionary as well to determine if a word exists. So if we have players with an S on the end, and player hasn't also been found, then it will be looked up in the list, and if it does exist, then we know that player is a word, so we can take off the S.
We've got some more results.
Oh, so we finished doing the second page now. So once we finish the stemming, this is the reason that it takes so long, because the word frequency statistics is a huge file of 50,000, I think, words. And at the moment, just the very basic version of the program is just a linear search through that, which is horribly inefficient. And one of the first things that I wanted to do, if we had more time, we didn't manage to, was do a binary search or speed that up in some way. Obviously, it'd be fairly easy to swap that in. So that's really why. So for every word in a page, it has to search through a list of 50,000 words to find it. That's why it's taking so long. But you can imagine it'd be fairly easy to speed that up. So that's what we're doing. So we have the stemmed words, and we then score them based on how common they are in natural language. Like I said earlier, less common words are given a higher weighting because they're more subject specific, we imagine. The actual distribution of the weights was a bit, there was a lot of tinkering going on there, and we didn't find any sort of really theoretically proven ways of doing it. The way that we did it in the end was just kind of exponential with frequencies in the frequency list.
About to lock itself.
And we also normalise the scores for each word by the page length, so that we can compare it to the scores we get from other words. Because when we generate the top, we're finished. When we generate the top 10 words per page, we link them into the words generated from the previous pages. So you can, as you can see, that's not going to work, is it? In each page, the word cricket came quite high up. So it was the third top word in that page, and the third top word in that page. Whereas in the final list of results that we output, cricket is the top word there because it appeared in all 3 pages. So the scores of each word across the pages are merged into the final list. So this is the list here that we output from those 3 pages. It's 30 words, the 30 top words from those 3 pages. That is then saved and can be FTP'd across to the server.
So why is there 30? Is it because there's 10 from each?
Yeah.
Okay.
That again is just a heuristic that we used. We just picked the number 10 and went with that. We found it got us fairly good results. Can be customised.
Okay, so now what I'm going to do is send this keywords.key file that we've created across to the recommender engine, which is done via FTP. We've got a script for that, which is just FTP put, which will literally just push. Sorry.
So presumably this process would be automated?
Yes, you could obviously automate it, but for the purposes of the demo and explaining through
fine,
it.
yeah.
So now that has been pushed onto the recommender engine. Is that?
Let's just explore.
Maybe you would want to stop the process and see if the key arrived and show them.
So basically we have 3 threads running in parallel over here. One is actually which is doing the recommendation and the crawler as well. So I'm just trying to find where exactly the file was transferred. So every time it says no files found with .key extension, that means that thread did. It's basically polling to see when the file arrives on the TP. But anyways, once it does find the file, it generates the recommendation file. In this folder, recommendations. So that's the file generated.
Yeah.
Can't exactly find where it is on the console because there's like so many things going
Yeah,
on.
so it takes about a millisecond for it to analyze the keywords and give a recommendation. So,
So this is the file generated. Basically contains a
the
list of
URLs,
links.
yeah. So the top 10 results for the keywords that
And
we had
this is
received.
the index which we built is basically just on the BBC website, so it contains all the links from BBC. Basically, we were crawling BBC last night.
Yeah. Yeah.
So, and once they're generated, we can send it back
Mm-hmm.
by FTP GET request. Not sure.
Okay, cool. Yeah, I would just mention that.
Yeah, so as you can see, this most of the news that we had just seen there is between the England, the India series and the Australia, Sri Lanka series. And the top results are obviously the Michael Hussey retiring, that's when he announced it. And Shane Warne is obviously an Australian cricket, and then about the Sri Lankan cricket team.
So quite relevant
Relevant
recommendations.
matches.
So now, obviously, those results are on the recommender engine, and we want to be able to view them as our user. So we need to FTP them back to the Minimorph. So that's just, once again, through an FTP script, which is just our FTP GET script, which actually gets two files, recommendations.html, which is the HTML that the user can view, and also a .rec file, which is our own file type, which later we put onto FlowWorld to store our recommendations.
This is a list of URLs.
Yeah.
.rec.
Yeah, so now we have the HTML on here. The user will be able to view it. This is simply by typing in the IP address of the Minimorph, I don't know, like you do with your router on your home network. So if I just show you here. So there we go, we've got the My Minimorph. So we sort of envisioned the home page for the Minimorph. If you log in, you can change your recommendation settings and stuff like that. We haven't actually implemented any settings yet, but that would be a future thing. So if you go into my recommendations, you can see now we're actually viewing that on the Minimorph, so that's hosting that, the HTML, and you can go in and use it. I don't know, I'm interested in the BBC article, the top result, and there we go, I've got a result. And now if you looked at that page, that can also be analysed again and goes back to our recommender engine, etc., etc. So that's fantastic. So yeah, Aldo, do you want to put your results onto FlowWorld?
Yep,
so
sure.
do you want me to do it, or do you want to do
Yeah. So,
it? Okay.
so as you know, we managed to get FlowWorld working between the Minimorph and the FlowWorld server, and we implemented that with using an interface layer. So we created a program called Interface, and that sits on Imagination's libflow API. So what Jack is doing here now is he's taking that recommendations.rec file, and the program Interface is going to look through the file, look at the recommendation links in there, and upload those to FlowWorld.
So now they've been up, our recommendations are on FlowWorld, so they're on the cloud now. So
Right.
in theory, you could access them from anywhere or
Right.
such like.
Ideally, this would happen on the actual server, not the Minimorph. However, on the Minimorph side, it needs to get these recommendations, and it can do it using the interface layer as well. So the interface layer was designed to be multi-platform. So if we just do an interface get, it will actually get those recommendations back from FlowWorld and generate a HTML file similar to the one that you've just seen.
So that's everything for the demo.